Okay, activity 7b, this is about impulse. Question, this is just tips and tricks, or tips I guess, for how to solve the 4 questions of this exercise, or this activity. So question 1 is about billiards, so snooker or pool. You bounce a ball off the edge of the table called the cushion, so it's a rubber edge along the edge of the table, in order to achieve a better angle for potting another ball. A billiard ball with a mass and momentum given is hit towards the cushion and bounces back with another momentum given. The impact lasts for 0.011 seconds. Draw a vector to show the direction of the change in momentum of the ball. So the crucial point here is that momentum is a vector. The direction of that vector is the same as the ball's velocity. Now, the other crucial point is that change in any variable, in this case change in momentum p, equals p final minus p initial. And these are vectors, so we can put a little arrow over the top. Now, the best thing to do is actually draw these vectors to start with, just sketch them. So p final is not an arrow that way, in fact, although that's how we represent that it's a vector. It's actually an arrow back away from the wall. And p initial is an arrow toward the wall. Which one's supposed to be larger? It goes toward the wall with 0.105 kilogram meters per second of momentum, and it comes back with 0.095 kilogram meters per second. So in fact the momentum toward the wall, pi, is larger than pf. And so if we do our vector diagram now, delta p equals pf minus pi. So that's the same as plus negative pi. And negative pi, if we go back up here, is a vector that way, slightly larger than the pf. Okay, so delta p equals, and then what we've got is this way. Oh, sorry, it's not, is it? Pf is this one. So it's that one, followed by the slightly larger that one, and so this is the resultant delta p vector. Okay, if we now do part B, this should now be really obvious. Part B, calculate the size of the change in momentum of the ball. So we know it's the same as the size of the negative pi vector. Sorry, this is actually the pf vector, and this is the negative pi vector. So the size and change in momentum, the size of the change in momentum, you're going to get by adding up the sizes of these two vectors. Hopefully you can see this arrow. I did the crossy out thing. That's always bad in the video. Okay, so add sizes of the two, pf and pi. Calculate the size of the average force on the ball. So you're given here how long the impact lasts for, and you've calculated a size of delta p. So delta p equals ft is the equation you want, delta p being the change in momentum, the force being the impulse force, and the amount of time of the collision, or the time in which the change occurred, being t. So that's the equation you want to use. Part D, on another occasion, the ball travelling with a momentum of 0.1 kilogram meters per second rebounds at right angles with the same momentum. So this is the diagram for it here. The ball comes in, hits the cushion, comes off again, 45 degrees to the cushion either side, so it's got a right angle in between. The ball is in contact with the cushion for 0.05 seconds. So again, we're likely to have another impulse calculation. Draw a labelled vector diagram to show the direction of change in momentum of the ball. So same thing again. Delta p equals pf minus pi. Pf in this case is this way. So pf, let's just draw each vector initially. So pf and pi. Now negative pi is going to be this way, Right, so it equals PF plus negative PI. I just do this every single time, right? Every single time I write this equation for what the change in a variable is, and then if it's a vector, I rewrite the equation to include plus negative. And then when I do the vectors, I actually redraw the arrow as well. This gives me some likelihood of making sure I get the right answer. So delta P, and now I actually do the vector addition, so this way and then that way, and they're at right angles to each other, giving a delta P being this way. And I can tell you this is not surprising because the force that the cushion provides is a force away from the cushion, so delta P has to be in the same direction as that force. Note here it's with the same momentum. So delta P, so this is the same size. These side lengths are the same. And so we've done our labeled vector diagram. Oh, this is PF negative PI. Okay. That's part 1, 2. So I've kind of given you the complete thing. I could have just said, just do it like you did the first one, but this time it's 2D, but now you've seen it in 2D. Part 2, show that the size of the change in momentum is 0.14 kilogram meters per second. So this is just solving using Pythagoras. You've got 0.10 here, 0.10 here, whoops, 0.10 here. What is this side? Delta P. So you can't just go adding the two together or subtracting the two numbers. You have to use Pythagoras' theorem to work out the side length of that side. Calculate the size of the average force that acts on the ball. We've been given a time. We have, from here, we're going to have delta P. So you're going to calculate that, and then you're going to use, well, you've calculated it for part 2, and you're going to use it in delta P equals Ft. And now I'm off the bottom of the page. So let's just go a little bit over this way. Explain why the direction of the force on the ball is the same as the direction of its change in momentum. This really comes back, I'm not going to write it down, I guess I'll put it over here. So if you're trying to explain this, you're going to use Newton's laws, or that it's the force creates the acceleration, which creates the change in velocity, which creates the change in momentum. Okay. That was question 1. Now let's have a look at question 2. Uh, 2A. During a docking maneuver, a spacecraft of mass 5 times 10 to the 3, it's 5,000 kilograms, moves towards a space station with a momentum of 1.5 times 10 to the 4 kilogram meters per second. The direction of the craft has to be changed by 90 degrees. To do this, the maneuvering rocket delivers a thrust of 3,200 newtons and is fired for 7.8 seconds. Calculate the size of the impulse given to the spacecraft. So impulse, pull out an equation. The equation you want for impulse is change in momentum equals Ft. We have been given a force here, force and a duration, so we're going to be able to calculate the change in momentum using that formula. B. Draw a labelled vector diagram to show the direction of the force of the rocket. Now we're told that the direction of the craft has to be changed by 90 degrees. So it's the direction of its movement. Now I think that means we're going to have to say that we've got a velocity, if we've got a momentum before and momentum after, we can just as easily do a delta V equals Vf minus Vi. And that's the same thing as delta P equals Pf minus pi, because when it comes down to it, p just equals mv, and nothing's happening to the mass, so, or at least not that they're telling us. In fact, burning fuel will reduce the mass slightly, but I don't think they want us to deal with that. So, this being true means that we can take the momentum before equals an arrow this way toward the space station, and p after equals an arrow this way. Now, it's going to be pf minus pi, so we need a negative pi vector. And then we do our nose to tail addition for delta p. So delta p equals pf down plus negative pi this way. And so our change in momentum vector, so this is pf, this is negative pi, and our change in momentum vector, delta p, is this vector here. Calculate the size. Oh, we've done that. Draw a labeled vector diagram to show the direction of the force of the rocket. Okay. Now, it doesn't say that the rocket is going at the same speed each time. If we assumed it was, then this is 45 degrees, but I don't think it's requiring us to do that. Calculate the size of the momentum of the spacecraft at the end of the maneuver. Okay, so this time, what we've got to know is that delta p, we've been given a impulse force. So delta p magnitude comes from part A. Okay, and we know the magnitude, so pi magnitude was given to us 1.5 times 10 to the 4. And here's your vector diagram. So you know this one and you know that one. That means that you can use Pythagoras' theorem to work out the final momentum. How do we know that this is a right angle? That's going to be the question that someone is going to ask. Well, in the drawing here, there is a right angle shown between the initial path and the final path. Okay, so that's question 2. Just turn this around so we can have a look quickly at, actually it won't, I'll leave that the way it was and cover it up with the book so I can look at question 3. A glider is propelled into the air by devices which have different graphs of force against time as shown, and the force F becomes 0 in all cases after the same time t. Okay, so which one would transfer the greatest momentum to the glider? Explain your answer. Well, here's the rub. Delta P equals Ft. Now this, usually what we do is we're assuming with this formula that this is the average force and the complete time, okay? And that represents the area under a force time graph. This area here is delta P, okay? So a rectangle is governed by its side lengths, so the area of a rectangle governed by its side lengths. So delta P, the area here, is represented by the area in a force time graph. Here we have these force time graphs, so whichever one has the highest area will have the highest delta P, the highest change in momentum. Now, which one's got the highest area? Well, A has this square plus this triangle. B is less than A because it's just, it has this rectangle plus the triangle above it. B has just the rectangle, so A is definitely greater than B. C is a triangle up to the right here. Well, if we transposed that and thought about it on A, it would be the triangle would fit completely inside here, so it can't be C. D looks even smaller, and E fits entirely within A as well. So, which one of the devices would transfer the greatest momentum to the glider? We can think about those ideas and answer it. It's going to be A, but think about how you're going to explain it. Question 4. The graph shows the force on a ball of mass 0.085 kilograms while being hit by a bat. The bat causes the ball to change its direction by 90 degrees. 90 degrees, so that's like the ball comes in, gets whacked by the bat, and goes off this way. Okay. The speed of the ball as it approaches the bat is 9.6 meters per second. Now I know that we have now got enough information to calculate the original momentum of the ball, okay, because we've got a mass and a velocity. So I think we can calculate pi, and we know its direction, and pi magnitude is going to be found using mv and the information given in the question. Okay, that gives you pi, but we want the change in momentum of the ball, so that's got nothing to do with this. That's just something I think we can calculate. So this is not the answer to question A. The answer to question A is going to be found, as we did for question 3, by thinking about this graph. So the change in momentum is the area under this graph. So area equals delta P, right? That's how you're going to solve this, and you're going to, for the part B, which I think is much bigger than it perhaps looks, you're going to have to consider a vector diagram to work out part B. Part B is bigger than it looks. So what there you're going to do is say, okay, it comes in, I'm going to calculate using pi. So it comes in at pi, it goes out with pf. Therefore, what is delta p? And then that will give you a magnitude. You'll have a magnitude of pi and a magnitude of delta p, and that will give you pf. And for that, you're going to need to what you're going to need to do, so you're going to have calculated delta p from here. Well, actually, you're going to, what is pf is what you're going to say. And your vector diagram you're going to do using the delta p equals pf minus pi. So this is your classic situation where you, that's the same as pf plus negative pi. Now pf is down, and negative pi, well, pi is that way, so negative pi is this way, and so delta p is this way by doing the vector addition. This is pf and this is negative pi. Okay, and this is a right angle because it said in the question that it changed its direction by 90 degrees. And now we have, from part A, we have delta p, right? And we can use this to calculate the length pi, and we can use this to calculate the velocity. So we use Pythagoras to calculate, first we've finished part A. Second, we calculate the initial momentum to put on here. Third, we use Pythagoras' theorem to calculate the final momentum. Fourth, we use P equals mv to calculate the velocity. There you go. That's the end of activity 7b. Hopefully that's been useful.